In this video, we're going to talk about the nomenclature of aldehydes and ketones, and we're going to talk about reactions forming the hydrates, enol, ketotartarism. We're going to go over the mechanisms for such reactions, synthesis problems, oxidation, reduction, Grignard reagents, pretty much most of the things you need to know about aldehydes and ketones, imines, enamines, how to prepare them, Wittig reaction, or some people call it the Wittig reaction. But let's begin. Let's start with the nomenclature of aldehydes and ketones. So here we have a ketone, and this is an aldehyde. Both compounds have a carbonyl group, which is a C double bond O group. The aldehyde is always at the end, and the ketone is usually somewhere in the middle. So this is the ketone. So to name it, you want to count the carbon atoms in the parent chain. So this is 1, 2, 3, 4, 5. So instead of saying pentane, which represents 5 carbons, it's pentanone, but specifically 2-pentanone, because the ketone's on carbon 2. Now for aldehydes, because the carbonyl group is always at the end, it's always going to be number 1, so you don't have to say it's number 1. So there are 6 carbon atoms in this structure. So to name it, it's simply called hexanol. So let's try some more examples. Go ahead and name this particular ketone. And then you could try this example as well. So for the example on the left, you want to count from the side that's where the carbonyl is located. So we want to count from the right side. We want to make sure the carbonyl have the lowest number possible. So the chlorine's on carbon 5, so it's going to be called 5-chloro dash 2, and 7 represents heptane, so heptanone. For this one, we have an aldehyde, and we have a bromine on 4 and a fluorine on 5, so bromo comes before fluoro, so it's going to be 4-bromo, 5-fluoro, and then hexanol with an Al at the end. Go ahead and try these examples. So here we have a ketone that's directly attached to a ring. So it's a 5-carbon ring that's cyclopentane, but instead of cyclopentane, it's cyclopentanone. Now this has to be carbon 1, so we don't have to say 1-cyclopentanone, because any substituent attached to the ring is relative to that carbonyl group. So if the carbonyl group is automatically number 1, you don't have to specify it. So this is simply called 3-methyl cyclopentanone. Now for our next example, this is still carbon 1, 2, and 3. So we have a double bond on carbon 2, so we can call it 2-cyclohexene with an En because it's an alkene, and then one. Now we can also say, some textbooks may write it this way, cyclohex 2-ene, and then they might put 1 one. You might see that in some textbooks. But for this example, we don't have to specify where the carbonyl group is located. Whenever you see a CHO, that's basically this functional group. It's an aldehyde. And Aldehydes have to be at the end, so they can't be directly attached to the ring. So here we have it outside the ring. So this group is a cyclohexane, and here we have a 1-carbon aldehyde, so it's called cyclohexane carb aldehyde. Make sense? Now this one, we have a benzene ring, and we have an aldehyde functional group, so it's called benzaldehyde. Now there's some common names that you want to be familiar with. Now for this example, the IUPAC name is 2-butanone because we have a carbonyl group on number 2. But we can also use a common name for it. Here we have a methyl on the right side of the carbonyl group, and we have an ethyl on the left. So putting it in alphabetical order, it's ethyl, methyl, ketone. That's the common name for that molecule. Now here's some other names that you need to be familiar with. This is known as acetone. It's a 3-carbon ketone. Here we have acetophenone. So when you have a 6-carbon benzene ring as a substituent, it's called phenyl. And aceto usually refers to 2 carbon atoms. That's an aceto group. And here we have a ketone, so we could see acetophenone. The phenol part comes from phenyl, and here we have the "-one" for the ketone. And here is our last nomenclature example. You also may need to know this for your test. This is known as benzophenone. Now phenyl is a benzene ring, 6 carbons as a substituent, but benzyl is 7 carbons. It's the benzene ring plus 1 carbon on the outside. So if this is the phenyl part, that's the 6 carbon benzene ring, the benzyl would include this benzene ring with this extra carbon on the outside, because benzyl represents 7 carbons, and plus we have a ketone, so thus we have the "-one" part of the name. So those are some things that you just need to know. Now sometimes you might get more complicated nomenclature problems where you have to know the names of different substituents. Now I'm not going to name this entire molecule, but I do want to show you what the names of these substituents are. Okay, so the first thing you need to do is find out which group has the highest priority. If you have a carboxylic acid, that's going to have the highest priority, and the parent name is going to be based on that. But in this case, it's the aldehyde. Aldehydes have more priority than ketones. And this is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So instead of saying decane, is decanol. Now, as a substituent, we know that CH3 is called methyl. So we have an 8-methyl group. NO2 is known as nitro. OH as a substituent is hydroxy, so it's 4-hydroxy. OCH3, it's very similar, but it's called methoxy because it has an O and a methyl group. NH2 as a substituent is called amino. And a ketone as a substituent is known as oxo. So those are some things that you want to keep in mind. So now let's talk about physical properties of aldehydes and ketones. So let's say if you have these three compounds. Sometimes you might get a question on the test to ask you, which of the following three compounds have the highest boiling point? Now, the one that has the highest boiling point is the one that has the most intermolecular forces. Butane is nonpolar, so the only type of intermolecular force that it has are London dispersion forces, aka van der Waals forces, which is the weakest of the intermolecular forces. Now, this ketone is relatively polar. So polar molecules, they have dipole interactions, and dipole interactions are stronger than dispersion forces. But this alcohol has hydrogen bonding. Any molecule that has hydrogen bonding is very polar. So in addition to having dipole interactions, it has hydrogen bonding, which is stronger than dipole interactions. It's a special case. So the molecule that's going to have the highest boiling point is the one that has hydrogen bonding. The boiling point of this molecule is like above 100. For acetone, it's like 56, and for butane, the boiling point is 0. As you can see, the one that has hydrogen bonding has the highest boiling point. So aldehydes and ketones, they have their boiling point exceeds that of nonpolar molecules, but it's less than those that have hydrogen bonding. Now, sometimes you might also get asked, like, which of these molecules have the greatest solubility in water? Now, the ones that are most soluble in water is the polar ones. So this alcohol has a high solubility in water. Butane has a very low solubility in water. The reason being it's nonpolar, and water is very polar. So like dissolves like, so water and butane, they don't mix very well. Now, you can dissolve acetone in water. It's relatively polar, so acetone has a higher solubility than butane, but less than that of 1-butanol. So we can say it's somewhat soluble. So now let's say if you have two aldehyde molecules, one of which has more carbon atoms than the other. Which one has the higher boiling point? So if they both have the same functional group, then look at the number of carbon atoms. The one that has more carbon atoms usually has the higher boiling point. This is due to the fact that it has increased intermolecular forces, specifically London dispersion forces. So the more carbon atoms you have, the greater the boiling point. And if the boiling point is higher, the vapor pressure is lower. So this is going to have a low vapor pressure. Now, which of these molecules have a greater solubility in water? What would you say? Is it the one on the left or the one on the right? Now, it turns out that this molecule on the left has a higher solubility in water. The reason being is it's because it's more polar. Now, you might be wondering, why is that the case? Because they have the same functional group. This part of the molecule is polar. However, this part, those three carbon atoms, are nonpolar. But here we have a huge nonpolar section. And the greater the carbon chain, the more nonpolar it is. So that's why it has a low solubility in water. Keep in mind, carbon-hydrogen bonds are nonpolar. So that's enough for the physical properties of aldehydes and ketones. So now let's talk about their relative reactivity, especially with water. So this is formaldehyde. And if we put formaldehyde in water, it's going to form what is known as a hydrate, which looks like this. If we put acetaldehyde in water, it can also form the hydrate. But notice that the size of the arrows are relatively equal in this case. the equilibrium value for the first reaction is about 1,000, 2,000, somewhere in that area. For this one, it's close to 1. So this reaction is reversible, the second one. And let's say if you have acetone and you put it in water, acetone doesn't react much towards water. So the equilibrium favors the formation of acetone rather than the formation of the hydrate. And we're going to talk about why that's the case. So for this reaction, K is very small, like maybe 0.002. So there are two factors that you need to know regarding the reactivity between aldehydes and ketones. First thing is that aldehydes are more reactive than ketones, as you can see. Formaldehyde is way more reactive than acetone. The first reason is due to steric factors. Hydrogen is smaller than a methyl group. A methyl group is more bulkier than hydrogen. So therefore, it's very easy for water to attack this carbonyl group. And because that carbonyl group is more accessible, aldehydes are more reactive than ketones. So that's the first reason. The second reason is electronic factors. This carbon is partially positive, and because it's attached to an electronegative oxygen atom, which is partially negative. So oxygen pulls electron density away from this carbon atom. So this carbon atom really wants electrons. And if you take electrons away from it, you're going to make it unhappy or less stable. But if you give it electrons because it wants it, it becomes more stable. Relative to hydrogen, a methyl group is considered a weak electron donating group. So a methyl group partially satisfies this starving carbonyl carbon. So it donates electron density to it, making it less electrophilic, thus less reactive. So that's another reason why aldehydes are more reactive than ketones, because they don't have the electron donating methyl groups. So the more methyl groups you have, the more electron donating groups you have. Thus the carbonyl group is less reactive. So let's go over a practice problem. Let's say if we have these compounds and you want to rank them in order of increase in reactivity. So from least reactive to the most reactive. So which of these compounds is the least reactive? We know ketones are less reactive than aldehydes. So let's look at the three ketones that we have, which are these three. So between these three, you want to find out which one has the bulkier groups. Here we have a total of 6 carbon atoms, not including the carbonyl group. So this is the most bulkiest ketone that we have. So this is the least reactive. This is going to be number 1. This ketone here is the second most bulkiest one. As we can see, it has 5 carbon atoms outside of the carbonyl group. This one has 4. So this is number 3. Now, between the remaining 3 aldehydes, the most reactive is this one because of electronic effects. It has 3 fluorine atoms on that carbon. So those fluorine atoms is going to pull electron density away from the carbonyl group. And when that happens, when it pulls electron density away from it, this carbon atom becomes more partially positive, thus more reactive towards water. So this is going to be the most reactive, so we'll say number 6. Now between these two, this is number 5 because it has an electron withdrawing group, which makes aldehydes more reactive. CH3's electron donating groups, they make aldehydes less reactive. So here, this is just an ethyl group, so that's an electron donating group. And so that's going to be number 4. It's less reactive than number 5. So you might see questions like that in which you have to rank the aldehydes and ketones in order of increasing reactivity. So what we're going to do now is we're going to go over a mechanism for the formation of the hydrate. So feel free to pause the video and see if you can do this yourself. We're going to do one under acidic conditions and the other under basic conditions. So I'm going to draw H3O plus like this. It's an oxygen atom with 3 bonds. It has 1 lone pair and a positive charge. Now the carbonyl oxygen is attracted to the acidic hydrogen. So it grabs the hydrogen and the OH bond breaks. Because oxygen is more electronegative than hydrogen, it pulls the electrons toward itself. So now we have a protonated ketone, which is activated towards nucleophilic addition. Nucleophilic addition simply means that you're adding a nucleophile to an electrophile. So water is going to behave as a nucleophile when it attacks a carbon atom. As it attacks this carbonyl group, this pi bond breaks, and so we get an OH. And here we have an O with 2 hydrogens. Whenever oxygen has 3 bonds, it has a positive charge. And what we need to do is remove one of those hydrogen atoms with another water molecule. So this water molecule grabs a hydrogen, this bond breaks, returns back over here. So now we have 2 alcohol groups. So now this is our hydrate. So that's the mechanism under acidic conditions. Very simple. So now let's try one under basic conditions. So what do you think is going to happen here? Well, we know oxygen has a partial negative charge, but carbon has a partial positive charge, which means that hydroxide is attracted to the carbonyl carbon. Opposites attract. So this hydroxide is going to attack the carbonyl carbon, and this pi bond is going to break, just like before. So under basic conditions, the nucleophile attacks first. Under acidic conditions, well, the nucleophile will be the carbonyl group, but it grabs the hydrogen first. So you have protonation. So this is what we have here. Now keep in mind, this is probably dissolved in water as well. So the oxygen with the negative charge is going to grab a hydrogen from water, regenerating our hydroxide catalyst. And so we have a hydrate again. So as we can see, under acidic or basic conditions, you can still get the hydrate. Pretty much these H3O plus and hydroxide, they act as catalysts and they speed up the reaction. So now we're going to go over the enol-keto tautomerism. So let's say if we have a ketone, it can convert into an enol, which looks like this. It's a double bond with an alcohol. So that's the word enol. En for alkene, Ol for alcohol. Now let's say if you have a diketone. It too can convert to the enol form. And it looks like this. As you can see in the first example, equilibrium favors the ketone. Pretty much roughly about 99% is in the ketone form, and less than 1% is in the enol form. However, when you have a diketone, if I remember correctly, I believe the numbers are 24% and 76%. But as you can see, this enol form is relatively stable, and I forgot the double bond, but here it is. The reason for that is due to this hydrogen bond, as we can see here. So that hydrogen bond, it stabilizes the enol form, thus increasing the equilibrium concentration that exists, or at equilibrium. Now there's another example, and that would be in this particular ketone. What do you think the enol form is for this ketone here? What we need to do is create a new double bond, which I'm going to highlight in blue, and then convert the carbonyl group to an OH. Notice that it's phenol. Now, phenol is aromatic, so therefore it's extremely stable. So pretty much more than 99% is in this form. Maybe close to 100. But as we can see, due to the aromatic stability of the ring, that enol form is extremely stable. So under normal conditions, usually the ketone form is stable, but the enol form can be the major product, so to speak, if it's stabilized by hydrogen bonding or by the formation of an aromatic ring. But now let's talk about the mechanism for the conversion of a ketone to an enol. Under acidic conditions and under basic conditions. So let's start with H3O+. Using H3O+, take a moment and see if you can come up with a mechanism that can convert acetone into the enol that we have here. So let's draw H3O+. Now this mechanism is actually very similar to the one in which we used earlier, where we converted acetone into its hydrated form. The first step is the same. Whenever you have an acid, the molecule will be protonated by the acid. And so here, once again, we have an activated ketone. Now, to get the hydrate, we use water as a nucleophile, and water attack the carbonyl group, and that's how we can get two alcohol molecules on that carbon. But if you want to get the enol, you don't want water to act as a nucleophile. Instead, you want it to act as a base. This red hydrogen that I drew, it's an alpha hydrogen. It's relatively acidic. And this water is going to grab this alpha hydrogen, and the carbon-hydrogen bond is going to break. Those electrons will move towards in between those two carbon atoms, causing this pi bond to break, whereby those two electrons will return to the oxygen. So now we have an OH with 2 lone pairs instead of 1, and we now have a double bond. And here, this water, it lost the hydrogen. So, H2O plus lost the hydrogen and it turned into water. And now that water molecule, it gained the hydrogen. So now it returned back into its original H2O plus form. So therefore, H2O plus was initially consumed, but it was reproduced at the end, which makes it a catalyst. So thus, it speeds up the conversion of a ketone to an enol and vice versa. But that's the mechanism of how to convert a ketone to an enol under acidic conditions. But now let's try under basic conditions. So go ahead and propose a mechanism for the formation of this enol under basic conditions. Now, to form the hydrate, what we did is we attack the hydroxide acted as a nucleophile, attacking the carbonyl carbon. But instead, we want to go for the alpha hydrogen if you wish to draw the enol. So hydroxide will grab this hydrogen. Those electrons will move here, and this bond will open, just like before. The only difference is the hydroxide attacks first. So now we have a double bond and an oxygen with 3 lone pairs. Now typically, hydroxide is usually dissolved in an aqueous environment like water. And since water is present, this oxygen with a negative charge can grab a hydrogen from water, regenerating our hydroxide catalyst. And so now we have an enol. So that's how you make it under basic conditions. So now let's talk about acetal and ketal formation. So let's say if we have acetaldehyde we're going to add methanol. This is going to give us a hemiacetal. So we're going to have one alcohol group and one OR group, or OCH3. And it can react with another alcohol, in this case methanol. And we're going to get two OR groups, or two OCH3 groups. So this is a hemiacetal. It's halfway. And this is an acetal. Technically speaking, acetals, they come from aldehydes. You get it when you combine an aldehyde with an alcohol. By the way, starting from the acetal, if you add water, it will drive the reaction back to the left. And keep in mind, if you continue to add water, it can go to its hydrated form, which, let's see if I could fit it here. For acetaldehyde, this reaction is reversible. It's like a 1-to-1 ratio. K was close to 1 for that reaction. So you can definitely get to hydrate, so watch out for that. And by the way, for these reactions to work, typically they have some sort of acid catalyst. So you might have methanol with an H plus catalyst. Now let's say if we have a ketone. If we add an alcohol to it, we're going to get something called a hemiketal. Ketals come from ketones. And if we continue to add more alcohol, we'll get a complete ketal, which has two OR groups. As you can see, acetals and ketals, they both contain a carbon that's attached to two single bonded oxygen atoms. It looks like a diether, so to speak. Now, throughout your textbook, you might notice that the word ketal is not used very often. And most textbooks, they just refer both of these molecules as acetals. So you hear terms like an acetal protecting group, which would actually look like this, but this name is actually kind of old, so they don't always use the word ketal. They just might use acetal to refer to this form or this form. But technically speaking, the acetal comes from the aldehyde, the ketal comes from the ketone. So now, what do you think will happen if we mix acetone with ethylene glycol, which looks like this, with an H plus catalyst? Now this reaction is reversible, but what do you think the product will be? It turns out ethylene glycol it works as a protecting group, and you're going to get something that looks like this. Now this reaction is useful because it prevents the ketone from reacting, and if you need to remove the protecting group, all you need to do is add H2O with H plus or just H3O plus, and you can get back to the ketone form. Another similar reaction is this one. Instead of using two alcohols, you can use a thiol. And you're going to get a product that looks very similar. But if you add Raney nickel to this compound, it actually reduces the substance into an alkane. So that's one way you can convert a ketone to an alkane. We'll talk about other ways too. If you use H3O plus or a mixture of water and H plus with mercury chloride, it can remove the thiol protecting group, and so you can go back to the ketone form. So let's work on some examples. What do you think the major product of this reaction will be? Let's say if we add H3O plus to it. So take a minute, pause the video, and see what product you think this might be. So if we had H3O plus, we can see that this is a protecting group. We have an acetal, or specifically a ketal, since this came from a ketone. There's two carbons here. For it to really be an acetal, it should be a hydrogen, but most textbooks will call it an acetal protecting group. What we need to do is, pretty much, we need to remove this section here and replace it with a ketone. The other product will contain these two oxygen atoms and these three carbon atoms. So it's going to look like this. Let's draw the three carbon atoms first, and then add the two alcohol groups. So instead of ethylene glycol, in this case we have 1,3-propane diol. So those are the products for this reaction. What about this one? Let's say if you add ethanol with an acid catalyst to cyclopentanone. What is the major product? Well, if we add one alcohol at a time, we can get a hemiketal and then a ketal. So first we'll get the hemiketal. One part will be in OH, the other part will be in OR, in this case OCH2CH3. But keep in mind, this could continue. If we have excess ethanol, then we can get two OR groups. We can get a ketal instead of a hemiketal, which will look like this. Now the last question on this topic has to do with the mechanism. Go ahead and propose a mechanism for the formation of this protecting group. So go ahead, take a minute, and see if you can do it. So anytime you have an acid, step one, you want to protonate the compound with the acid. So now we have our activated ketone, and it's ready to react with something. So then this alcohol is going to attack this carbonyl, and this pi bond is going to break. So now we have an alcohol. We have an oxygen that's attached to two carbons and has another OH. But this oxygen still has a hydrogen on it. And keep in mind, whenever oxygen has three bonds, it has a plus charge. Now, think of what we need to do. Our goal is to get rid of this alcohol. The only way to do that is we need to protonate it with a hydrogen and turn it into water, which is a good leaving group. And OH by itself is not a good leaving group. So we're going to use the solvent to transfer a hydrogen. And basically the solvent is ethylene glycol. So another ethylene glycol molecule is going to grab this hydrogen, and then this bond's going to break. So let's say that molecule eventually moves and gets over here. So then that protonated ethylene glycol molecule, or another one that's near its vicinity, is going to transfer the hydrogen to the OH. So this oxygen is going to grab the hydrogen, and this bond is going to break. So what we now have is an OH2 group, which is a good leaving group, and we have this. Now, let's think about what should happen. Option 1, this oxygen could attack this carbon and then kick out the water. That looks like an SN2 mechanism, where the nucleophile approaches from the back and kicks out the leaving group. Option 2, the leaving group could leave, generate a carbocation, and then a nucleophile can attack. So, what is the most likely mechanism here? Well, if we look at the substrate, it's secondary, plus it has this oxygen, so it's relatively hindered. Hindered substrates are not really good for SN2 reactions, and plus it's under Prodi conditions which favor SN1 rather than SN2. So the leaving group should leave first. However, this leaving group could be assisted by this oxygen here. Because this oxygen is already connected to that carbon, it can form a double bond, which could cause water to get kicked out or pretty much leave. And if that happens, what we now have is this. So now this oxygen has a plus charge. And so this carbon can be attacked by the other oxygen. As we can see, this structure has a resonance form because this bond can go back to the oxygen. Whenever you draw a resonance form, make sure you put a double arrow. So what we have is a resonance stabilized carbocation. So this oxygen, which is partially negative, is attracted to that carbocation, and so it bonds with it. And now that this oxygen has a plus charge, it's relatively acidic, so another ethylene glycol molecule is going to come in and take away this hydrogen. And so that's the mechanism for the formation of the protecting group. That's how you form it. So now, let's move on to another topic, and that is cyanohydrin formation. Let's say if you have a ketone and you wish to add HCN under mildly acidic conditions. What is the product of this reaction? And how can we show a mechanism for it as well? It turns out that the product of this reaction is an alcohol and a CN group. This is a nucleophilic addition reaction because we're going to add a nucleophile to the carbonyl group. Well, eventually. The first thing that happens under mildly acidic conditions is the oxygen is protonated by the hydrogen. And so now it's activated towards the nucleophile. So the nucleophile here is going to be cyanide. Now keep in mind, both the nitrogen and the carbon has a lone pair, but the carbon has a negative charge. Carbon is more nucleophilic than nitrogen, so this carbon attacks here, and then that bond breaks, and that's how you get the cyanohydrin, which looks like this. Now, if you were to add a strong acid like H2O+, it can hydrolyze the nitrile and convert it into a carboxylic acid. So now we have this molecule. So I'm going to redraw it like this. So let's say this is carbon 1, 2, 3. That's 1, 2, 3. On 2 we have a methyl group and we have an OH. So this compound, which is the same as this one, is known as an alpha hydroxy carboxylic acid. One carbon away from the carboxylic acid is known as the alpha carbon. This is the beta carbon. So as we can see, we have a hydroxyl group on the alpha carbon, so it's called an alpha hydroxy acid or carboxylic acid. Now let's see if we can form the cyanohydrin under basic conditions. So in this case, we're going to have cyanide. This time it's deprotonated, and we're going to have water as a solvent. So go ahead and show the mechanism for the formation of this compound. So the first thing that the nucleophile is going to do is going to attack the carbonyl group, and then that bond's going to open. So now we have an oxygen with a negative charge, and then we have a CN. And then the oxygen with the negative charge is going to react with water. It's going to grab a hydrogen, expel a hydroxyl group. And so we get this. And that's the end result for that reaction. So now we're going to go over oxidation and reduction reactions. But we're going to start with reduction reactions first. So this is another type of nucleophilic addition reaction. Let's say if you add sodium borohydride, NaBH4, it can reduce aldehydes and ketones, and it converts them into alcohols. So knowing that, go ahead and predict the product for this reaction. So all you got to do is draw the same carbon structure and then just simply replace the carbonyl group with an alcohol. And that's how you get the end result. So let's say if you have an acid chloride. By the way, NaBH4 can reduce aldehydes and ketones or anything that's more reactive than aldehydes or ketones. So like acid chlorides, it can reduce as well. However, it doesn't reduce esters and carboxylic acids. So if we add NaBH4 to an acid chloride, this is a two-step process. In the first reduction step, the Cl is replaced by a hydrogen, and then the aldehyde is further reduced to an alcohol. But to understand these reactions, we need to work with the mechanisms. So let's start with the first one. Let's propose a mechanism for the conversion of acetone into rubbing alcohol or isopropyl alcohol. So NaBH4, we have a boron that has 4 hydrogen atoms, and boron usually likes to have 3 bonds, kind of like aluminum. But when it has 4 bonds, it has a negative formal charge. Now, formal charge and partial charge, they're different. Boron has an electronegativity value of 2.0, and for hydrogen is 2.1. So hydrogen is slightly more electronegative than boron. So, intrinsically speaking, the hydrogen bears a partial negative charge. Boron bears a partial positive charge, even though it has a negative formal charge. Whenever hydrogen has a negative charge, it's known as hydride, and it's therefore nucleophilic. When it has a plus charge, it's just a hydrogen atom. It's like an acid. But here, because it has a negative formal charge, the hydride is nucleophilic and is therefore going to act as a typical nucleophile and attack the carbonyl carbon, which is partially positive. Remember, opposites attract. And then this bond is going to open. So thus, it's a nucleophilic addition. We're adding a nucleophile to a carbonyl carbon. So then this is going to be an oxygen with a negative charge. And here's the hydrogen that we added. Now this reaction, oh by the way, there's an Na+. The sodium has a positive charge because boron has a negative formal charge. The last step is to protonate the oxygen. And this gives us the alcohol. So let's try another example. NaBH4 can react with an acid chloride by adding 2 hydrogens instead of 1. So for this one, let's show the mechanism for this reaction. So here's the BH4 ion, and somewhere there's an Na+, so boron has a negative charge. So one of the hydride ions attack the carbonyl carbon, and then this bond is going to break. So we have what is called a tetrahedral intermediate at this point. And here's the hydrogen. Now the chlorine atom is a good leaving group, so what the oxygen is going to do is going to reform the double bond and expel the leaving group. So what we now have is an aldehyde. So sodium borohydride reacts again. So we have another BH4 ion, and it's going to react with this aldehyde. Turn it to an alkoxide ion. So now we've added 2 hydrogens so far. And in the last step, we can protonate the alkoxide ion with water. So in the end, we get a primary alcohol. So that's how NABH4 work, and also the other one, lithium aluminum hydride. They reduce carbonyl carbons by the addition of hydride ions. Now, lithium aluminum hydride, it's the stronger version of NABH4. Not only it can reduce esters, ketones, and acid chlorides, but it can also reduce esters and carboxylic acids, something that NABH4 can't really do. Now, we see that reducing a ketone or an aldehyde, you only need to add one hydride ion. And for the acid chloride, we added two hydride ions. An ester is at the same level as an acid chloride. It requires two hydride ions. The end result of this reaction, pretty much, all you need to do is cleave this bond, and you're going to get an alcohol. Replace the carbonyl oxygen with an OH, and this other part, which is going to leave, it's going to leave as an alcohol as well. But let's show the mechanism for this step. So just like boron, aluminum has a negative formal charge, and lithium has a positive charge. And then one of the hydride ions attacks the carbonyl carbon. Now, chlorine was a very good leaving group. That's what makes acid chlorides extremely reactive. However, OCH3, the methoxy group, is not really a good leaving group. Nevertheless, it still could leave though. And because it's a poor leaving group, esters are much less reactive than acid chlorides. So this oxygen forms a double bond, and then it's going to expel the OCH3 group. So now we have an aldehyde. Now another AlH4 ion can also reduce this aldehyde. So now we have an alkoxide ion by means of the addition of two hydride ions. And typically, step 2 would be using H3O+. Once we add H3O+, the oxygen is going to grab a hydrogen. So we now have an alcohol. And also the methoxide ion, which this one, it left as OCH3-. As soon as we put H3O+ in a solution, it's going to pick up a hydrogen and turn into methanol. Now, if you have a carboxylic acid, and if you add lithium aluminum hydride, followed by H2O+, this too would create an alcohol. That will be the end result. So this part is going to leave. In the last example, it left as methanol. In this example, it leaves as water. It's going to grab a hydrogen and become H2O. So let's go over some examples. Go ahead and draw the end result of the following reactions. So go ahead and predict a major product. So for each of these, if you have an aldehyde or a ketone, simply replace the carbonyl oxygen with an OH, and that's going to be the end product. It's better if you redraw the carbon structure first, and then replace the carbonyl oxygen with an OH. So as you can see, each of these require the addition of one hydride ion. So I'm going to show that. Now for esters, acid chlorides, and carboxylic acids, they require the addition of two hydrogen ions. So go ahead and predict the major product for these reactions. So for the acid chloride, what we're going to do is we're going to get rid of the leaving group, the Cl. We're going to redraw these 4 carbon atoms on the left. So 1, 2, 3, 4. We're going to replace the carbonyl oxygen with an OH. And we're going to add 2 hydrogens to this carbon. So 1, 2. Those are the 2 hydride ions that were added. And the Cl is the leaving group. So same thing for the ester. We're going to redraw the carbon structure. We're going to get rid of this group. So we have 6 carbons, 2, 3, 4, 5, 6. We're going to replace the carbonyl oxygen with an OH and add 2 hydrogens on that carbon. Now the group that was kicked out is phenoxide. But if we add H3O plus at the very end, which is usually the second step following lithium aluminum hydride, we're going to add a hydrogen to this oxygen. So the other side product is phenol. And the same will be the case for this one. So this part is going to be the same. All we need to do is convert the carbonyl oxygen to an OH and add 2 hydrogens. And this part, it's going to leave as water. We're just going to add a hydrogen to it. So plus H2O. So that's how you can quickly get the products for that reaction. But now let's work on a synthesis type of problem. Let's say if we have a molecule that contains both a ketone and an ester. What reagents do we need to produce the following molecule? But not just that one, but these as well. Okay, so let's look at the first one. In the first example, we want to reduce the ketone, but not the ester. So what reagent do we need to reduce the ketone but not the ester? We need a mild reducing agent, in this case NABH4. It can reduce ketones, but it can't reduce esters and carboxylic acids. Now if you look at the next example, we want something that will reduce both the ketone and the ester. So we need a stronger reducing agent, in this case lithium aluminum hydride, which is usually followed by H3O+. NABH4, you can add H3O+ at the second step, or you can mix it with water under basic conditions. But let's just put H3O+ for the second step. But now, what about the third example? How can we reduce the ester but not the ketone? Think about that for a moment. If we use NABH4, it will reduce the ketone. If we use lithium aluminum hydride, it's going to reduce both. So how can we do this? The key is we need to use a protecting group. Ketones are more reactive than esters. So what you want to do is you want to add ethylene glycol with an H+ catalyst. Because ketones are more reactive than esters, ethylene glycol will selectively react with the ketone, forming an, specifically really called a ketal, but most textbooks will refer to it as an acetyl protecting group. And the ester will be exposed. So now we need to use a strong reducing agent, lithium aluminum hydride, because out of the two, only it can reduce the ester. And then once we use lithium aluminum hydride, what we'll have first is something that looks like this. The ester is now converted to the alcohol, but we still have the protecting group on it. So our next step is to add H3O+ to remove the protecting group. And now we will get this product. So step 1 was ethylene glycol. Add the protecting group. Step 2, lithium aluminum hydride to reduce the ester to an alcohol. Step 3, H3O plus to remove the protectant group and regenerate the ketone. So now let's go over Grignard reactions. So let's say if we have acetone and we wish to mix it with ethyl magnesium bromide. Now you need to understand that whenever you have a carbon attached to a metal, typically the metal has a positive charge, but the carbon is usually negatively charged. So this carbon is partially negative, which means it's nucleophilic rather than electrophilic. So just like the hydride ion, it's going to do a nucleophilic addition reaction. So this nucleophilic carbon is going to attack the carbonyl carbon, and then that bond is going to open. So as you can see, the mechanisms are very similar. And so we're going to add the ethyl group here instead of a hydrogen. And then the last step is protonation by H3O plus. So this is the end result of that reaction. Now we can also use an organolithium compound to do the same thing. So as you can see, the last example was a ketone, and with ketones and aldehydes we can only add one R group, just as when we use NABH4 we can only add one hydride ion to it. So instead of using a Grignard reagent, let's use CH3Li, which works very similar to a Grignard reagent. So keep in mind, what's really reacting is a carbon with a negative charge. I mean, it's attached to the lithium, but view it this way, it's easier to see it. So this CH3 with a negative charge attacks the carbonyl carbon, and then that bond breaks. And the mechanism is very similar. So here's the R group that we're adding. And then finally, the last step, the alkoxide ion that's formed is going to grab a hydrogen from H3O plus. So Grignard reagents and organolithium reagents, they reduce ketones and aldehydes into alcohols by the addition of carbon atoms, or of some sort of carbon atom. And NABH4 reduces it by adding hydride ions. So go ahead and try these reactions. Predict the major product of each reaction. So for the first example, if you quickly want to draw the major product, redraw the carbon structure. So we have 4 carbons. Convert the ketone into an alcohol and add your R group. In this case, the R group is everything except the MGBr. So we're just going to add a benzene ring here. And that's how you can quickly draw the end product for a Grignard reaction. So the next example, we're going to do the same thing. Let's start by redrawing the carbon structure. Let's reduce the ketone to an alcohol, and then we're going to add this R group. So we have 4 carbons, 2, 3, 4. And that's the end result for that reaction. Now sometimes you need to determine the reagent. So pretty much you got to work backwards. So if you notice, these 4 carbon atoms remain the same. The R group is this propyl group. So we're going to rewrite that and add an MGBr to it, or a lithium atom. So let's use a lithium atom instead of MGBr. But keep in mind, you got to take off Well, actually, just make sure to write it backwards. Add the lithium to this CH2 because that's where it's attached to the, that's where the carbonyl carbon was. Step 2, just make sure to add H2O+. So try this one. So let's say if we have this aldehyde and we wish to make this product. What reagent would you use? So we can see that the R group is this part of the molecule. So I'm going to redraw it but backwards. And then add MgBr to it. So that's step 1. And then step 2 is H2O+. So you just got to see what R group was added, and then that's how you can find the reagents. So now what if we react a Grignard reagent with an acid chloride? What's going to happen? Well, just like the mechanism with NaBH4 and lithium aluminum hydride, if you add a Grignard reagent to an acid chloride or an ester, it's going to add 2 R groups. So the mechanism is very similar. The methyl is going to attack the carbonyl carbon. We're going to get a negative charge, and we're going to add the R group here, at least the first R group. Now we have a lever group, so this oxygen is going to form a double bond and then kick out the chlorine atom. So now we have a ketone, but this reaction won't stop here. It will continue. So the Grignard reagent will reduce the ketone into an alcohol. So now we have an alkoxide ion, and we also have our second methyl group. At this point, there's no more leaving groups, so the only thing we can do is protonate the alkoxide ion with H3O+. So now what we have is a tertiary alcohol. So let's say if we have the following ester and we wish to combine it with phenyl magnesium bromide. So just keep in mind, whenever you react an ester or an acid chloride with a Grignard reagent, you need to add 2 R groups. So this is the leaving group. It's going to leave. So draw the exact carbon structure, without the OCH3 group. So that's just this part of the molecule. Now we know that the carbonyl oxygen is going to be reduced to an OH. And then at this point, you need to add your 2 R groups. Right now, this carbon atom has 2 bonds. It can form 2 more. So we're going to add 2 benzene rings to it. And that's going to be the end result for that reaction. So now let's say if we have a ketone and a carboxylic acid on the same molecule, what's going to happen if we add a Grignard reagent to it? The Grignard reagent can act as a base or a nucleophile. As a nucleophile, it can go for the ketone. As a nucleophile, it's going to attack a carbon atom. But as a base, it can grab a hydrogen. So what is it going to do? Act as a nucleophile or as a base? It turns out the Grignard is a very powerful base, so it's going to act as a base before it acts as a nucleophile. So if there's any acidic hydrogens that are available to take, the Grignard reagent is going to take it. So it's going to grab the hydrogen. The ketone is going to stay the same. So all we're going to have at this point is a deprotonated carboxylic acid. Now, if you have an excess amount of Grignard reagent, after all of the hydrogen atoms are removed, then any additional Grignard reagent that remains will now attack the ketone. and then eventually that will be reduced to an alcohol. And then you can add H plus at this point too. Now the grinder can also reduce the carboxylic acid um, if there's no more acidic hydrogens as well. So keep that in mind. But the ketone is more reactive than the carboxylate ion, because this oxygen, an O with a negative charge, is a very, very bad leaving group. Alright, so let's go over some other reactions that you need to be aware of if you're going to have a test on aldehydes and ketones. So you need to be able to prepare aldehydes and ketones from alcohols and other compounds. So you got to know your reagents. Now, so this will pretty much be a review of Orgo 1, important reactions that you need to know for this test. So let's say if you have a primary alcohol, how can you convert that into an aldehyde? So while you're thinking about the reagent that's necessary for that transformation, try to figure out this one as well. How do you take a secondary alcohol and convert it into a ketone? And let's say if you have a terminal alkyne, how can you make a ketone and an aldehyde from it? So to make an aldehyde from a primary alcohol, the reagent that you need is PCC. You can look it up, but that's what you need. You can also add PCC to turn a secondary alcohol into a ketone. So PCC is very common. You can also, PCC is a mild oxidizing agent. You can also use a strong oxidizing agent like sodium dichromate with sulfuric acid or some sort of acid catalyst. But I think PCC gets the job done. By the way, if you use this on a primary alcohol, in this case, that compound, it will oxidize it to a carboxylic acid. So if you just want to make aldehydes and ketones, PCC is the reagent of choice. Now, if you have an alkyne and you want to make a ketone, you need to use mercury sulfate with water and sulfuric acid. If you need to make an aldehyde, use it's a different version of BH3 and THF, peroxide, and hydroxide. This is the hydroboration oxidation reaction. But this would give you an aldehyde if you start from an alkyne, a terminal alkyne specifically. As you can see, mercury sulfate, water, and sulfuric acid, that reaction proceeds with more carbon-carbon addition, where the oxygen goes on the secondary carbon rather than the primary carbon. And this reaction is anti-Markovnikov. That's the regiochemistry. And the oxygen goes on the less substituted primary carbon. Now, another way you can make a ketone is by starting with a nitrile. What you want to do is you want to add a Grignard reagent to it. So this carbon is going to attack this partially positive carbon. The nitrogen is partially negative. And as the methyl group attacks it, the triple bond will reduce to a double bond. So we have a C double bond N instead of a triple bond N now. But the nitrogen has 2 lone pairs instead of 1, so it has a negative charge. And here's the methyl group that we added to it. And then following that, you want to use H3O+. H3O+ will convert this deprotonated imine into a ketone. But let's work on the mechanism for that. So this nitrogen first will grab a hydrogen. Whenever nitrogen has a negative charge, it's extremely basic. But under acidic conditions, a nitrogen with a lone pair is still a base, but it's a weak base now instead of a strong base when it has a negative charge. So it's going to grab another proton. So now we have a protonated iminium ion. And at this point, we have water since H3O plus lost the hydrogen atom. So now water is going to attack the carbon, and then one of the double bonds is going to break. So let me start on the next page. So here's the water molecule that we added. This nitrogen has two hydrogens, and because it lost the bond, it now has a lone pair. So we want to kick out the nitrogen and add an oxygen in its place, a double bonded oxygen atom. So to remove the nitrogen, we need to protonate it. So we're going to use water to transfer a hydrogen from the oxygen to the nitrogen. So another water molecule is going to act as a weak base, and it's going to remove this hydrogen atom. And then in the next step, since I don't really feel like redrawing this molecule multiple times, after we regenerate the H3O plus ion, this nitrogen is going to grab a hydrogen, and then this bond will return back to the oxygen. So now we have a protonated amine group, which is a better leaving group than NH2, and we have an OH. So now what the alcohol is going to do is going to reform a double bond, or not reform it, but it's going to form it, and at the same time it's going to kick out the NH3. So what we now have is a protonated ketone. So now we can use that NH3 because NH3 is a weak base relative to water. So it's more basic than water. So more likely it's going to grab this hydrogen. And now we have our ketone. So the overall reaction for this process, what we did is we started with a nitrile. And then we add a Grignard reagent. So it turned to an imine, which looked like this. And then once we add H3O plus, pretty much all we got to do is replace the nitrogen with an oxygen. So we now have a ketone. So that's how you can convert a nitrile into a ketone. So let's say if we were to use lithium aluminum hydride instead of CH3MgBr. So this R group, instead of being CH3, it's going to be a hydrogen, because lithium aluminum hydride reduces by adding hydrogen atoms. By the way, this nitrogen with a negative charge, you can pair it with magnesium, which has a +2 charge, and a bromide ion. So in this case, since we have lithium, which has a plus charge, it's going to be paired with the nitrogen that has a negative charge. But instead of adding the methyl, we're going to add a hydrogen here. That's the R group that we're adding. And then if we add H3O plus, this will convert into an aldehyde. So now you know how to make aldehydes and ketones from imines and from nitriles. So how do we go backwards? How do we take a ketone and make an imine? So let's say if you add NH3. What you need to do is remove water, and you're going to get an imine. So view it this way. You can draw H2N-H. So water is going to be removed, and then you just add the NH in place of it. So here's another example. Let's say if we have methylamine. So we're going to remove water. Here's H2O. And then we're going to add the N with the CH3 in place. So these are called imines whenever you have a carbon double bonded to a nitrogen. But whenever that nitrogen has an R group, it's also known as a Schiff base. So if you add a nitrogen that has at least 2 hydrogen atoms, you're going to get the imine. This is a primary amine, by the way. Now, if you add a secondary amine, you're going to get something different. Where you're going to get instead is known as an enamine or enamine, which looks like that. So as you can see, a carbon single bonded to a nitrogen, which we have here, is an amine, and we also have an alkene, so thus we have the en part of the molecule. So let's work on some examples. So starting with cyclopentanone, go ahead and draw the major product of the following reactions. Okay, so looking at the first example, we have a nitrogen that has 2 hydrogens, so we're going to get the imine instead of the enamine. So what you want to do is redraw the 5 carbon ring, and then replace the oxygen with a nitrogen. So take away the H2, and then add the R group that's attached to the nitrogen. So it's CH2, CH3. And whenever nitrogen has 3 bonds, it has 1 lone pair. So that's the product for that reaction. By the way, these reactions are reversible. And usually, to get the imine, that reaction is favorable under mild acidic conditions. You get the greatest concentration of imine, typically around a pH of 4 to 5. So you don't want to use a strong acid. If you use a strong acid like H3O+, it's going to go back to the ketone form. But you want to use a mild or weak acid, buffered at this pH. Now, if we look at the second example, we have a secondary amine rather than a primary amine. As we can see, this nitrogen has 1 hydrogen and not 2. So what we're going to get is going to look something like this. I might need some space for this one. So we're not going to draw a double bonded nitrogen atom. It's going to be a single bonded nitrogen atom. And it's going to carry this ring with it as well. It's still going to have a lone pair, but we're going to have a double bond. So this is the enamine. Now here we have a primary amine, as we can see by the 2 hydrogen atoms. So let's redraw the our cyclopentane ring. So it's going to be an imine, so we know we're going to have a double bond N, and then we're going to add the benzene ring to it. The R group it comes along for the ride. So that's the product for that reaction. So let's say if we have cyclohexanone, and let's say there's a methyl group here. And we add this molecule to it. We know we're going to get the enamine product. So we know it's going to be a single bond to a nitrogen atom, and we're going to add the rings, or those 4 carbon atoms around that nitrogen atom. But here's the question for you. Where will the double bond form? Is it going to form on the left side or on the right side? So let me draw both possible products. Are we going to get the alkene here, or is it going to be on the other side? To answer this question, you need to determine which alkene is more stable. Now, tetrasubstituted alkenes are more stable than monosubstituted alkenes. which means the more carbon atoms that you have around a double bond, the more stable it is. But you need to know which carbon atoms to count. You don't want to count the 2 carbon atoms that are part of the double bond, as indicated in yellow. You want to count the carbon atoms that are attached to those yellow carbon atoms that I've indicated. So, in the first example, those 2 yellow carbon atoms are attached to 3 other carbon atoms. So this is a tri-substituted alkene. So in the second example, let's identify the carbon atoms that are part of the double bond, and let's see how many other carbon atoms are attached to it. So we have this carbon atom attached to that yellow one, and this one too. So there's a total of 2 carbon atoms that are attached to these 2 double bonded carbon atoms. So therefore, this is a disubstituted alkene. Tri-substituted alkenes are more stable than disubstituted alkenes, which means that this is the major product. So this is the one that you want to draw for your answer. Now sometimes you might get this question. Let's say if you have acetone, and let's say if you have a substance that has many nitrogen atoms. What is the product for this reaction? So feel free to take a minute and discuss this. So which nitrogen atom do we use? Let's see, do we use number 1? It has 2 hydrogens, it's going to give us an imine product. Do we use number 2? It has 1 hydrogen atom, so that would indicate the formation of an enamine product. Or do we use number 3, which has 2 hydrogen atoms, and that would lead to an imine? One of them will lead to the right answer. The question is which one? It turns out that, well, before I give you the answer, think about which nitrogen is most nucleophilic. Which nitrogen really wants to attack this carbonyl carbon? The key is resonance. You see, nitrogen number 3 is tied up with the carbonyl group. This lone pair delocalizes into this carbonyl structure, and as a result, that nitrogen now has a positive formal charge. So this lone pair is busy. It's not really available to attack the carbonyl carbon. And the same is true with this lone pair too. It can also form a double bond and cause this to go that way. And so it's going to look like this. So it too can have a positive formal charge. However, this nitrogen on the side here, it can't delocalize into the carbonyl group. So therefore, its lone pair is always available to attack something. And so this is the nitrogen that's going to attack the carbon atom. So to draw the product, we're going to take away these 2 hydrogen atoms and the oxygen. So we know it's going to be an imine, so it's a carbon double bonded to a nitrogen, and we're going to just add the remaining part of this molecule. So this is the product for that reaction. The key is resonance. You want to know which nitrogen has a lone pair that is ready to attack something. Okay, so now let's go over the mechanism. So how can you propose a mechanism for the formation of an imine? Take a minute and see if you can figure this out. So the imine forms under mild acidic conditions. The first step is protonation. Once you have an activated ketone, then the nitrogen can be used to act as a nucleophile. Now granted, this nitrogen can act as a base. It can go for this hydrogen atom, but if we do so, we're going to go back to step 1, and we don't want to do that. So what we want to use is, we want to use the nitrogen as a nucleophile where it attacks the carbon atom. So now at this point, nitrogen has 4 bonds, which means it has a positive formal charge. Whenever an atom has a positive formal charge, any hydrogens that are attached to that atom is relatively acidic. So if we want to form the imine, our goal is that we want to get rid of the oxygen and replace it with a nitrogen. So to get rid of this OH group, we need to turn it into a good leaving group, which means we need to add a hydrogen to it. So we need to use a solvent to transfer this hydrogen towards the OH. So in the solvent, we have, the solvent's probably water. So we can have water mixed with NH3. But NH3 is a stronger base than water, so if there's another NH3 molecule around, likely it's going to be the one that's going to grab this hydrogen. And so now, when we combine this NH3 with this hydrogen, we now have NH4 plus again. And I'm going to start this on the next page. So now this nitrogen lost a hydrogen, so it has a lone pair. And the NH3 that grabbed the hydrogen is now in the form of ammonia. So it's a weak acid. So this oxygen is going to grab a hydrogen. So now we have OH2 plus. So now, nitrogen can use this lone pair to form a double bond and expel the water molecule. So at this point, we have a protonated iminium ion. And so we can use another NH3 molecule, or even water, to get rid of this hydrogen. So now we have an imine. So now let's talk about the mechanism for the formation of the enamine. Let's use this molecule because you're going to see it a lot in organic chemistry. So step 1, we need an acid catalyst. So let's use H+. Let's activate the ketone. And then after that step, this nitrogen is going to attack the carbonyl oxygen. So now we have an OH and a nitrogen attached to it. But this nitrogen has a hydrogen, so therefore it has a positive formal charge. So what's going to happen now? In order to kick out the OH, we still need to protonate it with a hydrogen. So we're going to use this molecule again to get rid of that hydrogen. So keep in mind, there's many of these types of molecules in the solution. So this nitrogen is going to grab this hydrogen, and this bond is going to break. And now that this nitrogen has 2 hydrogens, it can transfer it to the OH. So this oxygen is going to grab one of the hydrogen atoms. And so what we now have is OH2. And this nitrogen has lost its hydrogen, so it has a lone pair. So just like the imine, what it could do is it can kick out water. But it doesn't have to. There's many ways we can show this step. But let's say it kicks out water. So right now, it appears to look like an iminium ion. But keep in mind, this alpha hydrogen is relatively acidic. And so we can use another nitrogen atom to act as a weak base. And it can grab this hydrogen which is going to form this double bond, causing this to break. And so now we have our enamine product, which looks like this. So the key here is to, at some point, you want to remove this hydrogen. Now we could have done it in this step too. We could have used the base to grab a hydrogen, form a double bond, and kick out water if we wanted to. But the end result was still the same. So sometimes there's multiple ways to get to the product that you want. Now there's some other orgo-1 reactions that you need to remember if you're going to make aldehydes and ketones. And let's briefly review ozonolysis. So let's say if you have this alkene and you wish to add ozone with dimethyl sulfide. What do you think the product for this reaction will be? Well, the alkene is going to cleave, and what you want to do is add a carbonyl to each carbon atom that was part of the double bond, so those two. So on the left side we have 2 carbon atoms, so we're going to add a carbonyl group, and on the right side we have 3 carbon atoms. So as we can see, we get 1 aldehyde and 1 ketone for that example. So go ahead and try this example. So for this one, all we got to do is cleave this bond. On the left side, we have 4 carbon atoms, and on the right side we have 3. And then just add a carbonyl to both. So those are the 2 products that we get for that reaction. Now sometimes you might have compounds that have multiple double bonds. In such a situation, you want to split each double bond. So draw the exact carbon structure, but just disconnect the double bonds. And then add a carbonyl oxygen to each location where it was disconnected. So for every double bond that breaks, you're going to add 2 oxygen atoms in its place. And so we get 2 products. We have an aldehyde, which looks like this. And we have this compound, which I'm going to turn it into a straight chain. So there's 6 carbons. 2, 3, 4, 5, 6. On carbon 1 we have an aldehyde, and we have a ketone on 5 and an aldehyde on 6. So those are the products for that reaction. Now another way you can make a ketone is by means of the Friedel-Crafts acylation reaction. Now if you recall, what's going to happen is you're going to lose HCl, and you can connect the 2 together and you get this ketone. So that's how you can make a ketone starting from benzene using the Friedel-Crafts acylation reaction. So now let's go over the Wittig reaction, or Wittig reaction. So what do you think the major product for this reaction will be? By the way, this is called the ylide, or at least it's the resonance form of the ylide. Now, the Wittig reaction, or Wittig reaction, it's very good in converting a ketone or an aldehyde into an alkene. So I'm going to redraw it like this. To quickly get the major product, what we're going to do is connect these 2 groups together. So basically, we're going to replace this oxygen with this group. So one product is going to be PH3P with an oxygen, and the other product, it's going to be the 5-carbon ring, redraw this side, and then redraw this side, double bonded to a carbon with a hydrogen and an ethyl group. So that's going to be the major product for that reaction. So let's try some examples. Try this one. Now sometimes you might see the ylide in this form. This is the other resonance form, the more reactive version. So here carbon has a negative charge, phosphorus has a positive charge. But keep in mind, carbon could take its lone pair and form a double bond, in which case it will look like this. But you need to be familiar with the different forms because it might be presented to you on its test in a different way. So what do you think the major product for this will be? So to quickly get the answer, replace the oxygen with this group right here. So it's going to be double bonded to a carbon atom, which is this carbon, and that carbon has 2 methyl groups. And that's how you can quickly get the answer if you don't want to like restructure it. So now that you know that, try this one. So to draw this product, let's redraw our original carbon structure. We're going to draw everything but the oxygen. We're going to replace the oxygen with a carbon. In this case, this carbon. Now you need to keep in mind that carbon has a hydrogen and it has this R group. Now, let me put that in a different color. So since this is in a line structure, I'm going to try to draw it in a line structure. So the carbon atom is already here. And then we need to add 1, 2, 3, 4 carbons. So 1, 2, 3, 4. On the third carbon we have a methyl group. And here's the other hydrogen atom. Okay, so let's say if you have this aldehyde and you're given methyl iodide, triphenylphosphine pH3 or PPH3, and butyl lithium. You need to recognize that this is the Wittig reaction, but they didn't give you the ylide. What they gave you, or what you were given, is the reagents that you need to make the ylide. So before we draw the major product, let's go over the mechanism for this reaction. So the first thing that happens is triphenylphosphine, which is a phosphorus with 3 benzene rings or 3 phenyl groups. It's going to attack methyl iodide in an SN2 reaction. So this lone pair attacks the carbon and it expels the iodine atom. So now what we have is this. So whenever phosphorus has 4 bonds, it has a positive formal charge, very similar to nitrogen. Phosphorus is right below nitrogen under the or in the periodic table. So nitrogen and phosphorus, they're chemically similar. So because this carbon atom is attached to a positively charged phosphorus atom, it's slightly more acidic, and butyl lithium is a very strong base. So butyl lithium is basically 4 carbons, but the last carbon has a lone pair. It's nucleophilic because it's attached to a positively charged lithium atom. And that carbon atom is a strong base. It's like a Grignard reagent. It's going to grab a hydrogen. And when it grabs the hydrogen, these 2 electrons in this carbon-hydrogen bond is going to form this double bond. And that's how you make the ylide. Now once you have the ylide, it's easy to see what the product will be. We know that in the end we're going to replace this oxygen with a CH2. So our answer is going to be CH3 with a carbon and a hydrogen double bonded to a CH2. That's the product of this reaction. But let's do the mechanism for it. So keep in mind the ylide has another resonance form. So I'm going to redraw it. Carbon is more electronegative than phosphorus. I believe the electronegativity of phosphorus is 2.1 and that of carbon is 2.5. So because carbon is more electronegative, when one of the bonds break between phosphorus and carbon, the electrons will go towards the carbon atom. And so carbon would bear the negative charge and phosphorus will bear the positive charge. Now this concept is important to understand because it helps you to know where the arrows will go for the mechanism that we're about to discuss. So just to review, let's say if we have this hydrogen and we use a base. Carbon is 2.5, hydrogen's electronegativity is 2.1. When a base grabs a hydrogen, this carbon-hydrogen bond is going to break. Those electrons, is it going to go towards the hydrogen atom or the carbon atom? Now we know instinctively it goes towards the carbon atom, and the reason for that is because carbon is more electronegative than hydrogen, and that's where we get a carbanion. Likewise, let's say if we have a bromine reaction, like a bromine on a carbon, and let's say if it was an S1 reaction. Bromine has an electronegativity value of 2.8, so it's a little bit more electronegative than carbon. So when that bond breaks, bromine takes the electrons, pulls it towards itself, and so we get a carbocation instead of a carbanion. So whenever a bond breaks, the atom that is more electronegative pulls the electrons toward itself. So now let's continue with our mechanism. So let's draw the more reactive resonance form of the ylide, which is the one that has separation of charge. And we're going to react it with our aldehyde. So this carbon is partially positive because it's attached to an electronegative oxygen atom. So notice that the CH2 carbon is attracted to this carbonyl carbon because they have opposite charges. Like charges repel, opposites attract. So this carbanion attacks the carbonyl carbon, and then that bond breaks. So what we get now is something that looks like this. So we have a phosphorus attached to a carbon, which is the CH2 carbon, and this CH2 is connected to another carbon that has an oxygen, and that carbon has a hydrogen and a CH3. So this CH3 is right here, and this hydrogen is over here, and this CH2 is this one. So whenever oxygen has one bond, it has 3 lone pairs, so it has a negative charge, and it's attracted to the phosphorus that has a positive charge. Once again, opposite charges attract. So this oxygen attacks the phosphorus atom, and it closes. So by the way, before it closes, it's known as a betaine, because you may need to know these names on your test. So now we're going to have an unstable 4-membered ring. Now, as you learned from Orgo 1, 4-membered rings are highly strained. They have a lot of angle strain. So this system will quickly decompose. What brings it together is the fact that we have opposite charges. And so that electrostatic interaction pulls the phosphorus and the oxygen atoms toward each other. So now, what's going to happen? How is this 4-membered ring going to break? By the way, this is called an oxophosphatane. To understand how this ring is going to break, we need to look at electronegativity. So oxygen has an electronegativity of 3.5, and for carbon it's 2.5, and for phosphorus it's 2.1. So we know that this is going to be one of the products. The phosphorus is going to be double bonded to the oxygen atom. So, and we know that we're going to form an alkene. So what this means is that this bond is not going to break. We're going to get another bond here if we're going to form a double bond between the two carbon atoms. And this bond is not going to break either because we're going to form a double bond between the phosphorus and the oxygen atoms. The bonds that will break is the bond between the carbon and the oxygen and the phosphorus and the carbon. So, let's focus on this bond, the bond between the carbon and the oxygen, since we know it's going to break. If it breaks, will it go towards the oxygen atom or the carbon atom? Well, we know that the electrons is going to go towards the atom that's more electronegative, and that is the oxygen atom. So when this bond breaks, it goes towards the oxygen and the phosphorus. So those electrons go between the phosphorus and the oxygen. And so that's how we're going to get the phosphorus double bonded to the oxygen. And then when this bond breaks, those electrons are going to go towards the more electronegative carbon atom. This carbon has an electronegativity value of 2.5. Phosphorus is 2.1. So it's going to go towards the CH2. So it goes that way. And so we get two products. We get the PH3, P double bonded to an O. As we can see, that's this region right here. And we're going to get the CH2 double bonded to a C that has an H and another CH3. And that's this part of the molecule. As you can see, it breaks down right here in the middle. And it separates into the triphenylphosphine oxide, which is this, and our alkene, which is the product of interest. So that's the mechanism for the Wittig reaction. So here's some other reactions that you need to be aware of. We're going to quickly go over it. If you have, let's say, an aldehyde, and you react it with a compound that contains silver, it could be silver oxide, Ag+, or even Ag complex with NH3. This is the Tollens reagent, and the silver ion in its +1 form is going to oxidize it to a carboxylate ion. Now usually this reaction occurs under mildly basic conditions, so if you want the carboxylic acid, add H3O+. So this is known as the Tollens test, or the Tollens reagent, and it's specific for aldehydes. It does not react with ketones. Now sometimes you may need to reduce a ketone to an alkane. There's three ways to do this. One way we covered already. Under acidic conditions, you want to use what is known as the Clemmensen reduction, which is zinc alloyed with mercury and HCl. So it's going to get rid of the carbonyl group, and it's going to add two hydrogens, which you can simply write it as cyclohexane. Now, another reaction that can accomplish the same result, but under basic conditions, is the Wolff-Kishner reaction. You need to add hydrazine, which is H2N NH2, or it can also be written as N2H4. And this will also reduce the ketone into an alkane. It can reduce aldehydes as well, by the way. Now the other one, which we covered earlier in this video, occurs under mild conditions. This is, instead of using ethylene glycol, we have to use this thiol, a molecule that has two thiol groups. And so initially we get this, but then we need to add Raney nickel, which will reduce it to an alkane. Now the last set of reactions that we're going to go over today is alkylation reactions. So let's say if we have cyclopentanol, you need to know that the alpha hydrogen, which is one away from the carbonyl group, is relatively acidic. So let's say if we use hydroxide. Hydroxide is a strong base, but it's not that strong relative to the acidity of this hydrogen. The pKa of a typical alpha hydrogen on a ketone, if I remember this correctly, it's like, I believe somewhere between 19 and 20. You can look it up. So this hydroxide can grab a hydrogen, and when that bond breaks, the electrons will go towards the more electronegative carbon atom. So we get what is known as a carbanion. This carbanion is relatively unstable, but it is stabilized by resonance. So this lone pair can form a double bond, and we can get the enolate ion. Now here's a question for you. Which of these two resonance structures is the major resonance contributor? Is it the carbanion or the enolate ion? So the real question is it better or is it easier for an oxygen to stabilize a negative charge or a carbon atom? It turns out that oxygen can better stabilize a negative charge. However, a negative charge in a carbon is more nucleophilic than a negative charge in oxygen. So even though this is more stable, the less stable form is more reactive. By the way, notice that I drew these arrows differently. If you use hydroxide, you only will get a small amount of the enolate ion. But if you use a stronger base like LDA, it's pretty much going to go towards completion. So hydroxide could work, but the yields will be low. So keep that in mind. Now, once we get this carbanion or the enolate ion, we can react it with something. We can use either resonance form. So we can react it with, let's say, an alkyl halide like methyl bromide. This carbanion will attack the methyl carbon and then expel the bromine. So this is known as direct alkylation. We can also use the enolate resonance form to do the same thing. But let's use ethyl bromide instead. So this oxygen is going to form a double bond, causing this double bond to attack the carbon, expelling the bromine atom. But in the end, we have a ketone with an R group, in this case, an ethyl group. So this time we're going to use LDA. LDA stands for lithium diisopropylamide. So it's a nitrogen that has two isopropyl groups and two lone pairs. So the nitrogen has a negative charge and lithium has a positive charge. So let's say if we use this particular ketone, and step one we use LDA, which works like hydroxide. It takes off the alpha hydrogen. And step two, we're going to use butyl-bromide. What's the major product of this reaction? If you quickly want to draw the product, replace the alpha hydrogen with the R group. So it's going to look like this. So let's try some more reactions. So let's say let's try this one. What is the major product for this reaction? So once again, just like before, replace the alpha hydrogen with this R group. That's going to be the end result. So try this problem. Propose a mechanism using LDA and methyl bromide to get this product. So step one, we need to remove an alpha hydrogen. So let's draw LDA like this. The lithium is a spectate ion, so we don't have to worry about it. This nitrogen is going to grab the hydrogen. And let's use the enolate form instead of the carbanion form. So this carbon-hydrogen bond is going to break. It's going to form a double bond and create the enolate ion. You need to be familiar with both resonance forms because sometimes you might get a multiple choice standardized test and you got to know what part of the mechanism is incorrect and which part is correct. So in the second step, this oxygen is going to reform the double bond, causing this double bond to be nucleophilic, attacking the methyl, and it's going to kick out the Br. And that's going to give us this product. So the mechanism is pretty straightforward. Now, what do you think will be the major product for this reaction? Let's say if we have cyclopentanone, and in step 1, we're going to use this molecule. You've seen it before. Step 2, we're going to add butyl-bromide. And in step 3, we're going to add H3O+. So in the first step, we know we're going to get the enamine. This is a secondary amine. And so it's going to look like this. And there's going to be a double bond. Now it's going to react with butyl-bromide, but the mechanism is going to be similar to that of the enolate ion with the methyl bromide that we did in the last example. So this lone pair is going to come down and form a double bond, and then this double bond is going to attack the carbon that has the Br, and it's going to expel the leaving group. So what we have now is an iminium ion, so the nitrogen has a plus charge, and we've added our R group. So now we're going to regenerate the imine group. So there's a hydrogen here. So let's say if we add water or H2O+. Once we add H2O+, this is going to be removed. It's going to go back to a ketone form. And that's going to be the end result if we use H2O+. But let's say if we didn't use H2O+. Let's say if we use water instead. Water could grab this alpha hydrogen, forming the double bond, and we can regenerate the enamine if we want to. So now, this enamine could react with something else. So notice that a second alkylation could occur. This could form a double bond and attack another methyl bromide. It's possible, but usually you just got to do the mechanism for one alkylation, but multiple alkylations can occur. Now keep in mind, there's another alpha hydrogen here, so we can alkylate the other side too. So what we need to do is control how much alkyl halide that we have. So if you add in butyl bromide, you want to make sure it's in a 1-to-1 ratio, so you can reduce polyalkylations from occurring. But if you add excess bromobutane, all of it can be replaced. So for example, let's say if we have methyl bromide and we added it in excess. All of the alpha hydrogens can be replaced. When that happens, this is going to stay in the iminium form. For it to be in the enamine form, you need to have at least one hydrogen that can be removed. So we'll get this. And then if we add H3O+, it's going to go back to the ketone form. So just watch out for multiple alkylations because they can occur. So that is it for this video, and thanks for watching. So I wish you well on your next tests on aldehydes and ketones.